Hi, NA Physics, it's Mr. Neff. Today, let's talk about power. But before we do, what did the pirate say on his 80th birthday? I'll tell you about that at the end of the video. Now, in a mechanical work sense, power is the rate at which you're going to do the work. So it is, anytime you have a rate, it's work divided by time, or whatever that is, divided by time. And so power is no different. It's going to be work divided by time. Now, the units on it, and this does actually get a tiny bit confusing, so follow me on this. The unit on it is going to be the watt. So there's a W for the watt, and it's confusing sometimes because work is part of this. But work is measured in joules, time is measured in seconds, of course, and so we nickname that the watt. So just be careful. The power will come out to be, some amount of watts. Just be sure that you realize that's the unit and not the work. Now, I have two video clips here, and they're both going to show a lot of work. They're both going to show work that goes along with lifting a car. First video clip is going to be the way you would probably lift a car, and the second is a way maybe they would lift a car in a garage. Now, here is a car jack that you would have in your car. Check this. There's some audio in the background, not super important. I'm going to talk over it. He's going to take that jack and he's going to place it on the car's frame right there between those two blue pieces of tape that he's placed on the car for reference. Now, it's going to take a little bit of time to get the car moving upwards. Now, I have this playback speed on 1.5 times, but the point is that using this kind of jack is going to take a little bit of time. So now what he's going to have to do is attach a handle to this. You'll see the handle coming in here in just a second. And then he's going to have to turn the handle around. But now, to apply a force that's human-sized, it's going to take some time to actually get the car going up there. And so he's cranking. And remember, this is even on sped up speed. So he did some work on that car. This, on the other hand, and this is also played back at 1.25 speed. This is going to be something like they might have in a city in a parking garage. And that's not a human lifting that, a human's pushing the button, but that is a motor that's lifting it. And you see that was a lot more work, but it was way, way quicker as well. And so I ask, which video shows more work? Well, the second video shows more work, of course. Why? Because you lifted the car up much higher, right? The change in potential energy here was just enough to get a new tire on the car. The other one, it was a huge change in potential energy because you were trying to park a whole nother car underneath it. So that's not really on point here, but it is true. But which video shows more power? Well, in a really long amount of time, so I'm going to put a huge T on the denominator of this fraction, we did a little bit of work. And here, in a really brief amount of time, we did a lot of work. Now, it's that rate that I'm focusing on here. You can see that this was a very powerful movement. Why? Because a lot of work was done in a very brief amount of time. And over here, this was not a very powerful movement. It was human size because compared to a machine, we're just not as powerful. We can't put out work at the rate at which a human would be able to, or a machine would be able to do that. So my point is, the amount of work divided by the time is the power. And even if on the video there was a point where they had only lifted the car up a little bit, and then the numerators would have been the same, but the times would have been very, very different, and so the powers would have still been very, very different. So power being that work or change in energy over time. As I said, the watt is the SI unit, but sometimes, especially if you're into cars, you'll hear about horsepower. Horsepower, it really started off as the amount of work that a horse could do, and at the rate at which a horse could do work. And that actually was devised by James Watt, which it's kind of funny that those are the same person was involved in both of those units. And so, yeah, there's a conversion factor between the two. Horsepower aren't SI, but you do see them a lot, especially with cars and other kinds of engines. Sometimes the change in energy divided by time is split up as work divided by time. And we all know that work is force dot displacement divided by time. Occasionally, you'll see that displacement over time turned into average velocity. And so you can see what I have down here, that power can also be calculated as force times the average velocity, that either something is forced to move on or is maintaining or something like this. I have one quick example for us. Here's a cheetah, and it can go from rest to 27 meters per second in 4 seconds. It's got a mass of 110 kilograms, and they say determine the average power. Well, it is working on itself. It's converting its food into its own kinetic energy, so it is working on itself. And that work has a rate. For a cheetah is impressive because that rate is very big. The time that it takes to get up to speed isn't very much. And so they say, what is the power of the cheetah accelerating its own body? So now I gave you 2 ways to calculate power so far in this video. I said you could do work divided by time, or you can do force times average velocity. And I want to show how to do both of those. I want you to stop the video and at least try one of those methods to get the amount of power in watts and the amount of power in horsepower. So please stop the video and then come on back. All right, we are back, and the power is going to be that work divided by time. Now, the work is, as we know, is a change in kinetic energy divided by time, or a kinetic energy final minus a kinetic energy initial divided by time. Cheetah started off at rest, so 0 initial kinetic energy. So all I'm going to do is half of the mass of the cheetah times the final velocity of the cheetah squared, and then I am going to divide by the time. If you go ahead and put the numbers in, the numerator of this will come out to 40,095 joules. And then you're going to divide that by 4 seconds, and you'll end up with 10,023.75 watts. Only 2 of those are really significant. You could do it a different way, though, too. You could have said the force necessary to accelerate this cheetah. Well, what force is that? Well, that's going to be equal to whatever the mass times the acceleration of the cheetah is. So I could say mass times acceleration times average velocity. So the mass is 110 kilograms. The acceleration is the change in velocity over time. It goes up to 27 meters per second from 0 in 4 seconds. And then the average velocity is going to be the average between 27 meters per second and 0. And so I'll add those together and divide by 2. If you go ahead and multiply all of this out, you're going to get, well, you're going to get an acceleration of 6.75 meters a second square, and then an average velocity, of course, of 13.5 meters per second. And so if you multiply all that out, guess what? You get exactly the same thing, 10,023.75 watts, or close with rounding. And there's our watts answer. Now, the conversion between watts and horsepower, remember I showed that just a little bit ago in the video, horsepower and watts. 1 horsepower is 746 watts. And so if you convert that, you end up getting 13 horsepower. Yeah, cheetahs are, I don't know if you can plow a field with a cheetah, but you sure could, you sure can see that it's, for the acceleration phase, it can accelerate like 13 horses. All right, I hope you learned a lot about power there today. And before we leave, what did the pirate say on his 80th birthday? Aye, matey. See you next time.